Hi, my name is Corey Deal. I am presenting on the log periodic trapezoidal toothed antenna, or LPTTA for short. The reason why I chose this antenna was for a couple different design parameters. The first one being a wide bandwidth for my antenna. I wanted to have an antenna that worked for a large spectrum of frequencies, and I also wanted it to operate at Wi-Fi frequencies, so 2.4 gigahertz and 5 gigahertz. The reason for this is I have some ESP8266s and ESP32s that operate at those frequencies. I thought it would be interesting to see if I could design an antenna that could interface with them. The last thing that I wanted to design the antenna for was I wanted it to be easy to match. So what brought me to these log periodic antennas was because in the book that we're using for this class, Bolaños mentions that these types of antennas are frequency independent and that they operate for a large spectrum. So to me what that meant was that they would have a constant impedance across a large band of frequencies, and I would be able to design an antenna that would be relatively small and easy to match to, so it fit all of my design criteria. Now, the four main examples that the Bolaños mentions is a spiral antenna, where the spiral is frequency independent, so the larger the spiral, the lower frequencies it can go down to, and then closer is higher frequencies. The same thing is for this log periodic circular antenna, where the length of this arc corresponds to what frequency that piece operates for, similar to a patch antenna where it will operate at lambda over 2, or half the wavelength, corresponding to the length of the antenna. That is this length for this antenna. And then this right here is the the high frequency for this antenna, and this is the lowest frequency of this antenna. And then this is a very common log periodic dipole antenna, where this is the low frequency and this is the highest frequency this antenna operates at. So all of these log periodic antennas, or as Bolaños calls them, scale invariant or frequency independent antennas, have a common property, which is that as you scale them, they still look the same. And that's why there's this fractal antenna here, which is that if you were to zoom in on this part right here, it would look the same as the larger curve right here. So fractal antennas start to pop up here for the same reason that the spiral antenna has this fractal property, where if you were to zoom in on it, it would still look the same. So another antenna that looks kind of like the ones that I was interested in is the Yagi, where adding more elements onto it makes it have higher directivity, but doesn't give it a higher bandwidth. So by adding in more elements to these log periodic antennas, you get more frequency bandwidth, which is what you can see here. Each tooth that you add onto these log periodic antennas, you get more bandwidth. So the more teeth out this way, the lower the bandwidth, or the lower frequencies you can get your bandwidth. And the more teeth you have going in towards the center, the higher frequencies you get on your bandwidth. Now, for the antenna that I chose to do the trapezoidal toothed antenna because I only had a straight edge to work with. I didn't want to go through the hard work of doing a circular design, since I had already done the circular patch antenna, and I found that took a couple hours to get a nice curve to my circular patch. So I felt like the circular toothed antenna would be much more time intensive to build compared to the trapezoidal antenna. The main difference is that the book, Bellani's book, does not cover as in depth these two antennas, so I had to do a bit of digging and research to figure out kind of how they worked. And what I came across is that each of these teeth kind of acts as like a patch antenna, where the length of this arc corresponds to what frequency this particular tooth operates at, similar to the middle length of this trapezoid corresponds to the frequency that this tooth operates at. You can imagine there being infinitely many equally scaled apart, so that way this trapezoidal planar tooth antenna would operate at a large range of frequencies. So, going to the theory of why these work, kind of a heuristic way of looking at it, Bellani says, if all physical dimensions are reduced by a factor of 2, the performance of the antenna will remain unchanged if the operating frequency is increased by a factor of 2. In other words, the performance is invariant if the electrical dimensions remain unchanged. Thus, if the performance is completely specified by angles, the performance would have to be independent of frequency. So what this means is that you can think of the patch antenna, where the length of the antenna corresponds to half the wavelength of the operating frequency. So this is half the wavelength right here. So if you were to increase the angle, you would be increasing the operating frequency of this antenna. Similarly, you can scale this antenna, which would also make this length longer, such that you would have a higher operating frequency. So by scaling or reducing the physical dimensions by 2, you are increasing the frequency by 2, since the wavelength of higher frequencies is smaller and the wavelength of lower frequencies is higher. Another way of thinking about this being scale invariant is if this went off to infinity, if you were to scale it down by 2, it would still look the same. So it would, in a sense, be scale invariant. Now, another thing that I wanted to mention real quick before we move on is he says that the electrical performance would be unchanged. Where is that? Yeah. So its electrical properties would be unchanged. So what that means to me is that if we were to scale this thing, its input impedance, or what it looks like as an impedance, would remain unchanged at all these different frequencies. And for the bow tie antenna, that frequency, that impedance can be determined by the elliptic integral, which is just another integral, and we could use numerical software to evaluate that, or a numerical method to evaluate that. So far, these types of antennas seem to have met all of my design criteria that I was going for, which made them seem like a good choice as intended to design. So going to the theory of that, as we said, by scaling the geometry of the antenna is the same thing as increasing the angle of the geometry. Now, this f of theta comma phi, I don't want it to get confused with the beam pattern of the antenna. This just happens to be the same notation for it that Bellani's used in his book, but it is not the beam pattern, it's the geometry of the antenna. So, what Bellani's walks through, which is the same as the origins of where this theory comes from, is he takes some partial derivatives, which is to get a functional equation for how this thing, or how these types of antenna function. So if you take the partial derivative with respect to the angle constant that you're adding onto this thing, k completely varies with the constant C, with the angle change, because increasing by scaling factor K is the same thing as increasing the geometry by C. So what that does is you just have the partial derivative of K with respect to C, and the geometry remains unchanged. However, when you take the derivative with respect to C of the geometry, you do a chain rule. Now, I was confused by this at first, but I realized that that was just the derivative with respect to the y coordinate, and then taking the derivative of phi plus c with respect to c is just 1, and that's where this comes from. Now, on the other side, if we're taking the derivative with respect to phi, k is unchanged, and we only vary the geometry, so that's why we have this here. Now, doing the derivative with respect to phi of the right-hand side, you end up with the exact same chain rule where you're varying the y coordinate, and again, this derivative is 1. So we have the exact same thing on the right-hand side for both partial derivatives of our equation here. And equating the two gives us this nice functional equation that describes the properties of these types of antenna. So a really nice thing about this geometric relationship is that if you divide by k on this side and you divide by the geometry onto the right-hand side, you end up with two expressions that have independent variables of each other. In other words, there is no theta or phi on this side, and there's no k or c on this side. So that means that I can vary how this thing scales, or how I choose this thing to scale, which we'll see is tau and sigma later, and then I can vary the geometry how I choose without affecting the scaling terms, as long as I choose these to be the same. Now, if I exponentiate both sides, we get an interesting property here, which is that we get the partial geometric differential equation of k, which is the scaling factor with respect to the angle scaling factor, is equal to the geometric derivative of the geometry with respect to phi. And this is the partial differential equation, or partial geometric differential equation, that these types of antenna must satisfy, which I thought was of particular interest. Now, if you solve this, you get that your geometry is equal to our chosen scaling factor to the power of phi times f of theta. And the f of theta is what we have a choice for. It could be whatever we would like it to be. It could be in the plane, it could be out of the plane, as long as we have this nice scaling relationship to the power of phi, then we are satisfying this property of scale and variance and frequency and variance for these types of antenna. And as an engineer, this is a really nice property to have, because that means that there's infinitely many types of antenna we can choose that meet these conditions. So I designed my antenna using HFSS just to have a computer software and see if it agreed with what I was choosing for my antenna. And what I immediately found was that the antenna design toolkit that we were using had an error that popped up where it would not generate, simulate, or run my antenna that I wanted to design. So I found that if you go to View, ACT Extensions, Wizard, and then click HFSS Antenna Toolkit, and that would pop up with almost the exact same thing, where you can edit the type of substrate you're using, your parameters, and you could edit the thickness, height, pretty much everything you needed, and then synthesize and generate the antenna. And what this allowed me to do was at least see what geometry that HFSS came up with, so that way I could compare it with my calculated one. So I did that, and HFSS generated this nice trapezoidal tooth antenna for me with angles 60, 30, and 30. And this happened to meet all of my calculations. The problem with HFSS still is that it would not it would not simulate my beam pattern, it wouldn't simulate my antenna gain, and it wouldn't simulate my reflection coefficient. So I had to rely on my tests, or my actual physical tests, to see what the antenna did and interpret what was happening from that. Now, as far as Belanis goes, he does not go into much theory on how this antenna works or how to compute the lengths, and neither does the documentation for HFSS. So what I did is I read a paper that corresponded to half the wavelength of the arc of the circular antenna equaling the length that the circles needed to be, or that the arcs needed to be. And I used that to generate an equation based off of trapezoidal geometry to determine the length of each one of these trapezoids, or length from the origin of each one of these trapezoids, based off of the angle, beta, the wavelength I was going for, and the scaling factor that I wanted to choose. Now, a nice thing that you're allowed to choose is sigma is the ratio between this length and this length from the origin, and then tau is the ratio from this length to your next tooth on the same side. And what I chose is for those to be the same. So in other words, sigma is equal to the square root of tau. And that's why there's a square root of tau here. So your lowest frequency determines your outermost tooth, and your highest frequency determines your innermost tooth. And by multiplying by tau, you can get to the next length that you need, and then multiply by tau again, that gets you to the next length. Multiply by the square root of tau gets you this length, multiply by the square root of tau again gets you to here, multiply the square root of tau gets you to here, multiply by the square root of tau gets you to the next length. And once you have hit the length of your highest frequency is when you can stop adding teeth, and you'll have an antenna that works over that wide of a range. Now, I didn't have time to test it, but I think if you want your antenna to work specifically at 2.4 and 5 gigahertz, which is what I was designing for, you could just cut off the corresponding teeth that you don't need in order to hit those frequencies. And you'll still retain the nice properties that we were discussing before, because it has that nice periodic scaling property to the power of phi. Now, I also accounted for in this equation if you take the speed of light divided by the frequency to get the wavelength, and the dielectric constant of the substrate I was using, which was 4003 C duroid. And pretty much this equation that I derived came up with nearly the same length that HFSS came up with for every single tooth. So as far as the parts go that I used some copper tape, probe feed, and 4003 C duroid as my substrate. And to me this seemed like the easiest way to construct it, since I could just take some copper tape, cut it out without having to go through the pains of peeling off really precisely the copper on top of this 4003 C duroid plate. Now, if I had a milling machine, then I could easily mill out a very precise, much better than I could do by hand, antenna, which I think would be more ideal for the construction of these types of antenna. So, my original test, I didn't make a incision here and cut between the negative side and the positive side. And this was because I wasn't sure if this type of antenna operated more like a patch antenna or more like a dipole antenna. So I tested this with the ground plane behind it first and the probe feed sticking through right here, and found this as my reflection coefficient, or S11 pattern, across several frequencies. What I noticed is it had kind of the same properties I was looking for, where it would be good from over a wide range. In this case, it was from 4 gigahertz up to 8 gigahertz. However, it had a couple divots that I was kind of expecting if this was a bunch of patches together, where this is one patch, this is another patch, this is the next patch, and so on up the ladder. And you see these spikes, another spike, another spike, and another spike as you go up in frequency, which I think is due to the dielectric constant of the material I chose. And this was okay, but it didn't meet the design criteria that I was going for. It didn't meet a nice flat reflection coefficient for several frequencies that I was going for. So what I did is I disconnected the two different sides, this side and this side, and I used the probe such that the probe feed was connecting right here and the negative side of the probe was connecting right here, and these two are disconnected like a dipole. And with that, I got the range of frequencies that I was going for, where this is 2.4 and this is 5, and notice how it's very flat along there. Now unfortunately it wasn't perfect because my cutout wasn't perfect, and for that reason I think that's why it wasn't perfectly flat along the S11 parameters for the frequencies I was going for. Just after the 5, it goes right up to 0 for quite a long ways until I got up to 9 gigahertz. So it seems like it's operating where I'd like to, but unfortunately this gives me a very high reflection coefficient for a large band of frequencies, which means that I have to match this antenna. So, whoops, going back a slide. So, I plugged the antenna into the spectrum analyzer. I noticed that unlike other antenna that I tested, instead of getting a loop in here or a couple loops in there, it was kind of like this nice circular band around one VSWR circle. Now, if this was perfect, I think that the response would be almost just one circle instead of going in a little bit and out a little bit. And that means that there would just be one voltage standing wave ratio over the entire range of frequencies that I was designing for. This seems really apparent for the 3 to 4 gigahertz band right here, where it's just one solid circle, and that's where I was saying that was mostly flat. So to me this means that with maybe a conical stub, I might be able to match this wide range of frequencies, since I'd just be matching one VSWR circle for a perfect antenna. However, for my specific antenna, I just probably try to match just the 2.4 gigahertz and just the 5, since that's what I was going for my personal home project. Alright, so looking at the radiation pattern, or the gain pattern from the anechoic chamber, I noticed that for two different orientations, these were both at 2.3 gigahertz, that I had two main lobes, which shows that this antenna, or this type of antenna, is highly directed in two directions. And this was with two different orientations, so I'm pretty sure that this lobe and this lobe are the same, this lobe and this lobe are the same, and then it seems like this is a side lobe right here and here. So perhaps with more of these antennae, I can get a higher gain and more directivity doing an array of them with a lower reflection coefficient, making it easier to match or no need to match. And I'd see that circle kind of go down to the center. At least that's my hypothesis. So, conclusions. The frequency-independent scaling angle-based antenna have a very nice theory that's based off of a geometric partial differential equation. There is a huge variety of them where all you have to do is pick the geometry and be sure that you fit the parameters of that differential equation such that you retain these nice properties. My antenna operated over a large spectrum of frequencies, and it had two main lobes that show that it's very directed and has a higher gain in two directions. It also only had one main VSWR circle if it was ideal, is my hypothesis. And if I were to use a milling machine, I would like to test that for a future project. So that was my antenna, and hopefully this gives some ideas on what to do if you would like to design your own log periodic antenna. Oh, computer, turn projector off. Okay.